Hello, hi all. I want to welcome you to today's lecture. Today will be the last the last lecture for this module, or for module 5. And today we'll be capping it off with looking at limiting reactant and the reaction yields. And this is a fallout to the last lecture where we talked about stoichiometry. So what basically we're going to be doing in this lecture is that we are going to be using our knowledge of stoichiometry and mole ratio of a chemical reaction to determine the limiting reactant and then to calculate the reaction yield of the reaction. All right, but before we do that, I have a beautiful quote here. The quote says, "Problems are nothing but wake-up calls for creativity." This is a beautiful quote. It says, "Problems are nothing but wake-up call for creativity." Oftentimes, when we encounter adversity, it tends to shape us, because we learn a great deal of lesson from it. That is just the message from the quote. Now, our learning objective here is just one learning objective will be addressed this time. We'll be using the mole concept and, of course, the factor unit method, just like we did with the stoichiometry, to do calculations on the limiting reactant principle and the reaction yield. We're going to use it to do those two things. Now, let us take it off from there. We'll start. What is a limiting reactant? What is a limiting ingredient? Of course, most of us cook at home. I like to cook all the time. Cooking is my hobby. Usually, whenever you want to cook, you have the formula for your cooking. You have your recipe. But something is usually not completely supplied. Something is limited in supply. And may that be the limiting reactant? Now, let's see what we have here. You see, I want to make a bicycle. And to make a bicycle, at any point in time, I need one frame plus two. I need one frame. I'm going to try to use different alphabet for this. I need one frame plus two wheels to make a bicycle. I'll call my bicycle BC at any point in time. So this is just like my stoichiometric balanced equation, which of course is one frame, two wheels will give me one bicycle. That's exactly equal to, so of course this is our arrow here represents equality sign. It now says, how many bicycle frames can you make if you have 3 frames and 4 wheels? Which is the limiting, which is the excess? Now, before I answer this question, let us just get to the next page and look at what is going on. Let's solve this problem here. In trying to solve those problems here, let's see. The first question says, of course, we know that from the formula that I was given there is that I need at any point in time, let me look at it again. I need one frame. I need one frame plus 2 wheels to make at least one bicycle. Now, and the problem says, the first one says, if I have 3 frames and 4 wheels, what am I going to make? So first of all, I'm going to try to see how much I'm going to make from my 3 frames. So if I have 3 frames, how many bicycles will I make? Let's start. Remember how we did stoichiometry by using conversion factor. So what I know now, my conversion factor I'm going to be looking at is the ratio between the frame and the bicycle. Of course, this is 1. Okay, let me try to use a different color to highlight those. Let me use a different color. So if I take off this thing, I'm going to try to use 1 frame, 1 bicycle. I'm going to take this off too. I'm going to put 2 wheels. This is my formula in this case. Now, of course, if I have 3 frames, first of all, it says if you have 3 frames, let me go back and make sure I have it. Okay, if I have 3 frames, 3 Fs, where am I going to? What will be my output of bicycle? Let me try it. Of course, again, I'm going to use the conversion factor as usual. So if I have 3 frames, what it means is I want to convert from 3 frames to 1 bicycle. That's the typical job I need to do here now. So what am I going to use? I'm going to use the mole ratio between frame and bicycle. And the mole ratio is, at any point in time, 1 bicycle will give me, is equivalent to 1 frame. Of course, because my frame is on the bottom, I can easily make a cancellation. Frame cancels frame. What it means is that if I started with 3 frames, I can make up to 3 bicycles. That's what I can make. And then what if I start with 4 wheels? How many bicycles am I going to make? Let's go back and see that. If I started with 4 wheels, let's say, if I have 4 wheels, I started with 4 wheels. Of course, let me look at the ratio. There is 2 wheels for every 1 bicycle. What it means, I'm going to have 2 wheels for every 1 bicycle. And again, if I cancel out, wheel cancels wheel, I'm going to be left with bicycles. So if I do my division on 4 over 2, it's going to give me 2 bicycles. Now, what it means is that if I have 4 frames, if I have 3 frames, I'm going to make 3 bicycles. If I have 4 wheels, I'm going to make 2 bicycles. Now, which one do you think is realistic? What is realistic at this point in time is that by the time I make only 2 bicycles, I would have run out of my frames. So for me to make up to 3 bicycles, I actually need 6 frames, but I don't have it. What it means is that this value, I cannot get up to this. I cannot get up to this. What I actually have that I need to make will be from what I've given. What is practical for me to make will be only 2 bicycles. And if I've done that, what it means is that I've converted, of course, my wheel to my bicycle. Here I converted my frame to my bicycle. That's basically what I did using the knowledge of stoichiometry. So what followed? Therefore, now, since this one represents the theoretical, these 2 bicycles represents the theoretical, or I can say the maximum possible bicycles I can make. That's the maximum or possible bicycles I can make. And therefore, we'll give it a name very soon. So since I'm going to run out of this one, but frame becomes, therefore, frame, or not frame, wheel becomes my limiting reactant. So my limiting reactant is going to, so my limiting reactant will be the what? The wheel. The wheel becomes my limiting reactant. And what will be my excess reactant? My excess reactant is going to be the frame. So what does that simply mean? Is that we've defined it. So what is now the limiting reactant from this knowledge? Let me go back to this and fill out this. So from what I have just done, it simply means that if I go back again, my limiting reactant is what? From here, my limiting reactant is the wheel, W, and my excess reactant is the frame. And how much bike is it possible for me to make? What I can make from this is the one that was made by the wheel, which is only 2 bicycles. Only 2 bicycles at this point. The 3 bicycle at this point is not feasible. The 3 bicycle at this point is not feasible for me to make this. But it's only feasible for me to make this. And therefore, that is the amount I can make given the ingredients I have. So I can only make 2 bicycles. And these 2 bicycles I can make is called the theoretical yield. And very soon we'll be talking about the theoretical yield of experiment. So this is the theoretical yield. I'm meaning that I cannot get up to 3 bicycles. I can only get up to 2 bicycles. So now if I define my limiting reactant, what is it going to be? The limiting reactant is defined as the reactant or ingredient that runs out first. That's my, and hence determines the output. The output, you can say product, or how much that can be made. That is what a limiting reactant is. So the limiting reactant is what tells you how much of the product you can get in a reaction, and not the excess reactant, because the excess reactant value is not a theoretical possible value. That takes us to some important terms we need to define before we move on. Now, Of course, usually the amount that is determined by calculation, which is the amount that is possible to be made with the theoretical yield, would always be greater than the amount that is being made in the laboratory. Now, the theoretical yield will always be more because theoretical yield is expected to be 100% that you need to make as you calculated when no product is lost. But such a scenario is usually not possible because what happens? The less product will be obtained, of course, than was calculated because side reactions and possible losses which do not give desired product of the reaction. And that introduces another type of yield, the actual yield. The actual yield is the actual amount that is obtained from the experiment or in the lab. If the one you obtain from the experiment or in the plant, it can be in the experiment, it can be in the plant, it can be just your outcome, the real outcome, given all the limit of experimental error and accident and everything. Whereas the theoretical yield is that amount that was calculated using the mole concept. That amount that was calculated using the mole concept and the limiting reactant principle. It represents the theoretical maximum. If I go back to this again, my theoretical yield in this experiment, the theoretical yield I got here is this. 2 bicycles is my theoretical yield. That is the maximum amount I can make because this 3 bicycles is not a possible value. So that is what we call the theoretical yield. And then, what is the percentage yield? The percentage yield simply is done with this formula. It is the percentage of the actual yield. The actual yield is what you did actually, practically, what you obtained. If you divide it by the theoretical yield, it gives times 100. Of course, again, I tell students, the theoretical yield is the 100%. It's always greater than the actual yield. But this is what you calculated from the limiting reactant principle. If you do your limiting reactant gives you this. That is what you get from the limit. And then this is what you get from the lab or experiment or in the plant, depending on where the production took place. That is what you get from there. Okay, now let's take it off from there. The first thing we'll be addressing today is the mole-to-mole limiting reactant. The mole-to-mole limiting reactant, of course, like we did in stoichiometry, we'll first of all take it from the simple to the complex. The mole-to-mole is the simple. So, and of course, remember again that when we talked about mole-to-mole, we do not need the molar mass because we use the stoichiometric ratio to convert from mole of A to mole of B. And let's take it off as a good example. Let's move on from there. Now, the first question says, how many moles of water are formed? Of course, it says the theoretical yield. It can be called the theoretical yield. It can be called the maximum amount. No matter how the name is phrased, it shouldn't confuse you. It says that can be made or formed when 25 moles of oxygen react with 19.5 moles of hydrogen according to the following equation. It now says determine the limiting and the excess reactant. Again, you know about the conversion factors from the stoichiometric lecture. If you've not watched that video, I advise you to go and watch that video because that is going to help you to understand this as a solid background. Okay, let's take it off from there. So what it means is that we apply our conversion. 25 moles of, I'm going to calculate the amount of water from 25 that will give me a particular mole of water. I will also calculate again from oxygen. So because the two ingredients we always give in a test student, the way you know you are in a limiting reactant problem is to look at your problem and see that the two ingredients you need in a reaction is given. These two reactions have only 2 reactants and both of them are given. Therefore, it must be a limiting reaction or a limiting reactant problem. So let's take it off. So I'm going to start with 25 moles. So 25 moles of oxygen. Of course, if I'm going to convert this, it's going to be 25 moles of oxygen. What's the mole ratio between oxygen and water? You have 2 moles of water over 1 mole of oxygen. And if you cancel that with my different color, moles of water goes, what do I have? I have 50 moles of water can be generated from oxygen. What amount of water can be generated from hydrogen. That is what we're doing next. In doing that next, so of course I start again, 19.5 moles of hydrogen, of course, will give me, of course, if you look at the mole ratio, 2 moles of hydrogen takes 2 moles of H2, 2 moles of water, H2O takes 2 moles of H2. And then again, if I cancel with my green, most of these cancel most of this. And when you multiply that, of course, it's going to give you 19.5 moles of H2O. Now, it now says, which one gives you the less number? You see, hydrogen gives me the less number of 19.5. What that simply means is that hydrogen is the limiting reactant. And the amount of water, the theoretical yield I can get, this is the theoretical yield. So this number becomes the theoretical yield. And the limiting reactant, LR, is what? Hydrogen, because it produced the least number of my product. And that is what is possible for me to get. And then what is my excess reactant? The excess reactant, ER, is the oxygen. Oxygen becomes the excess reactant. Oxygen becomes the excess reactant in that problem. All right. So I think I have it written, just not to be confused. I'm going to write the excess reactant and limiting reactant for the first time. So I'm just going to write it. So let me see. So the limiting reactant, L, limiting reactant, is hydrogen, and excess reactant is O2. So always pause the video, feel free to try out some problems and see how much you're going to do. Now we go to the next one. Similar scenario again. This is mole to mole limiting reactant. It says calculate the maximum moles. Again, the maximum moles will be the theoretical yield, the theoretical mole of PHR generated from 27.5 moles of P4 and 35.8 moles of hydrogen according to the following equation. Again, we start. The two ingredients we are given, we have 27.5 moles of P4 and 35.8 moles of hydrogen. So if we start again, it's going to be, I'm going to use my red. So it's going to be 27.5 moles of P4. Now, what do I have here? I have the mole ratio of P phosphorus to this to be 1:4. So it's going to be 4 moles of PH3 over 1 mole of P4. And when you do your multiplication well, you cancel, let's see, if you cancel this and you multiply it, you're going to get 110 moles of PH3. And then we solve the similar problem with this one. The next one, we go back. We have 35.8 moles of hydrogen. So we do with it. So it's going to be 35.8 moles of hydrogen. I want to convert it. Again, there are 4 moles of this guy, 4 moles of PH3 to 6 moles of H2. Again, this will cancel this, and it's going to give me 23.9 moles of PH3. Okay, so from there, our limiting reactant, now we look at the two value. Phosphorus gave us 110 moles, whereas hydrogen gave us 23.9 moles. What that simply means is that the value that is smaller will be our theoretical yield. That will be the maximum moles of PH3 that will be generated. So this becomes our theoretical yield. And then the limiting reactant is My limiting reactant is hydrogen, whereas the excess reactant ER is what? Excess reactant becomes P4. Alright, so feel free to try out these videos and then practice on this. That's usually good for you to pause the video, try it yourself, and come back to see if you're getting the answer. Then we move on from there. The mass to mass conversion. Again, this my flow chart is a familiar flow chart that you saw in the last lecture. So again, in the mass to mass, we're just expanding the mole to mole. That's exactly what is happening. We're expanding it from both sides, one way here and expanding it one way here. So what it means is that you have to first of all convert the mass of what you have to the mole of what you have before you now interconvert it between the mole of one to the mole of another using the stoichiometric ratio. So the best thing to do is to see a problem immediately and solve it. So the problem says how many grams of water, the theoretical yield, again, are formed if 14.7 grams of oxygen react with 10.0 grams of hydrogen according to the following equation. Which are the excess reactants and the limiting reactants? That we want to know. So first of all, we start with the first ingredient. The first ingredient we have there is hydrogen. That's what the first ingredient we have there. So we're going to start with that ingredient. So it's oxygen rather. All right, I start. So it's going to be, as usual, 14. I'm going to use my green rather. I like using my green, so I'm going to say. So it's going to be, let's start, 14.7 grams of oxygen. I'm going to try to draw my line. Let me use a better line drawer to see if that line is going to be beautiful. Okay, it was. And then, okay, then I'm going to convert this to mole. So I know that if I convert it to mole, it's going to be 1 mole of oxygen. Of course, remember again, we have to calculate the molar mass of oxygen, which I did earlier. So the molar mass of oxygen is 32.00. So the molar mass of oxygen is O2. So the molar mass is going to be 2 times 16.00, and this will give us 32.0. grams per mole. Then hydrogen, of course, is going to give us H2, 2 bracket 1.01. That gives me 2.02 grams per mole. And then what else? Water molecule. Of course, water is going to give you, there is 2 of these of hydrogen. So this 2 bracket 1.01 plus there is 16.00. This will give you 18.02 grams per mole. Just want to, in case there's a point you missed that, let me just put those up there for some people who might not get. Now, so converting to mole, this is going to be 32.00. Remember that? That's where we are. Grams of oxygen. Put this. I come back again. Now, what's the mole ratio between oxygen and water? It is 1:2, or you see put water on top. So water is going to be 2 moles of water over 1 mole of oxygen. And again, the last one, if I cancel, let me cancel a little bit. Grams, okay, I didn't put my oxygen here. Please, I'm going to use a different color. Grams of O2. So if I cancel it out, gram of O2 goes with grams of O2. Mole of O2 goes with mole of O2. We have moles of water. Then we're going to convert it to mass of water. What do we use? We're going to use the molar mass of water. So what that means is that a mole of water of H2O is going to be 18.02 grams of H2O. And again, if we can cancel out, let's see what it's going to give us there. With my green, we go with this. And then if you multiply everything completely, it's going to give you 16.6 grams of H2O. That is what we generate from 14.7 grams of oxygen. Then what can we get when we start from the hydrogen? Hydrogen is 10.0. Let's go and start that with hydrogen. So it's going to be 10.0 grams of hydrogen. I draw this my line. Now 1 mole of hydrogen, of course, will give you 2.02. That's the molar mass of hydrogen, grams of hydrogen. And then what's the mole ratio between hydrogen and water? 2:2. So it's going to be 2 moles of hydrogen will give us 2 moles of water, will give us 2 moles of hydrogen. And then we convert it to molar mass. What it means is that a mole of H2O will give us 18.02 grams of H2O. If I cancel all those things, let's say this goes with this goes with this, now this goes with this, and when you do your multiplication, you're going to get 90.1 grams of H2O. From here, it is clear and apparent that our theoretical yield, of course, the amount of water that will be produced, theoretically, it will be, this is the theoretical yield. This is the amount of water that will be generated in this reaction that's possible to be generated. And then the limiting reactant is going to be our oxygen. So here, the limiting reactant, of course, the LR is O2, and the excess reactant ER is hydrogen. So that is how we do this problem. You can always pause this video, solve this problem, and come and check it back for your answers. We go to the next one, problem 4. It says, how many grams of pH3 are generated when 10.35 grams of P4 reacts with 39.60 grams of H2 according to the following balanced equation, which is the limiting reactant? Again, we have to calculate the molar masses of this guy. I have to do it this time here. So it's going to be P4. I have to go back to my red. Now, so it's going to be P4, of course, will be, move it a little bit back, because I got some space now. So it's going to be P4 will be equal to, we have 4 times 30.97 grams. So this will give us 123.88 gram per mole of this guy. Then, of course, the next one, hydrogen, we did it earlier, but it's just 2 bracket 1.01. This will give us 2.02 grams per mole. And then the last one is pH3. Now pH3 contains phosphorus, which is 30.97 plus 3 times 1.01. That will give us 34.00 grams per mole. And then we start writing. First of all, remember again that we're given 2 ingredients. So we're going to take each of these ingredients and convert it to the mass of pH3. So let's start. We start with this one. So it's going to be 10.35 grams of P4. I'm going to draw my line. I want to convert it to moles. So it's going to be 1 mole of P4 equivalent to 123.88 grams of P4. And then 4 moles. Remember again, we've converted it to moles of P4. So we want to convert it from moles of P4 to moles of pH3. So the ratio is 4:3. So 4 moles of pH3 is to 1 mole of P4. 1 mole of P4. And then lastly, now we want to convert from moles of P4 to grams of, from moles of pH3 to grams of pH3. What it means is that a mole of pH3 is equivalent to 34.00 grams of pH3. And if I cancel everything I have, let's see. Grams of this cancel grams of this. Mole of this cancel most of this. Mole of this cancel most of this. And then my answer is going to be 11.36 grams of pH3. And of course, this is what I'm going to get. Then what am I going to get from the other one? Now, I'm going to try to expand this page a little bit. Now, I'm going to try to move this a little bit up. We don't need that space anymore. So, now, what do we have here? Now, okay, so let's do it. So what we're going to do here now is we start with what we're given. Let me see. Okay, let me try to make it where I'm going to be seeing. Okay, 39.60 grams of hydrogen. So let's go there. So it's going to be, we start again, 39. Now I'm going to use a different, my red as usual. So it's going to be 39.60 grams of H2. I want to convert this to mole of H2. So remember that a mole of hydrogen is equivalent to 2.02 grams of H2. And if I convert that again to, what's the mole ratio? 6:4. So 4 moles of pH3 will be equivalent to 6 moles of hydrogen. And then I'm going to convert that to the mass of pH3. So a mole of pH3 will be equivalent to 34.00 grams of pH3. And then if we cancel that, it's going to be this, we cancel this, this, we cancel this, and this, we cancel this. And when we do our arithmetic well, the answer is going to give me 444.4 grams of pH3. That is what I get. Now, if you look at these two numbers, it is very clear that phosphorus gave us the lowest value for water. What it means that this value is now the theoretical yield. And what does that tell? That tell you that what is the limiting reactant? From there, the limiting reactant is, so the limiting reactant LR, okay, I can put it here. So the LR is, the question they say, which is the limiting reactant alone? So the limiting reactant is going to be what? P4. P4 is our limiting reactant, because it is that one that gave us the lowest number. And this value we get here becomes our theoretical yield. 11.36 grams of pH3 becomes the theoretical yield of this reaction. We go to the next problem. The next problem says, how many grams of carbon dioxide, again, the theoretical yield. I keep putting this, in exam, I don't have to put this, but I keep putting this thing for you to know that no matter how the question is phrased, whenever you're doing the limiting reactant principle, the question is just basically you should calculate the theoretical yield. So let's take it off from there. Again, we have to do the molar masses of all these guys. So to do the molar mass of these ones, I hope you know how to do the molar mass by now. I may just write them out, then you can confirm the molar masses later. So I'm just going to write it out just for writing out sake, so that I don't have to spend a lot of time, because I don't want it to be bored. So it's going to be, no, that's what I'm using. So it's going to be, so my F, if you calculate the molar mass of Fe3O4, that is going to give you 240.55 gram per mole of that guy. And if you calculate that of carbon monoxide, it's going to give you 28.01 grams per mole. And if you do that of carbon dioxide, it's going to give you 44.01 grams per mole. So these are what we're going to get from all these guys. So now we start working. So the question gave us 48.4 grams of Fe3O4 and 14.6 grams of carbon monoxide. And that says, it says we should calculate how many grams of carbon dioxide formed. It also says which is the limiting reactant. It also says what is the yield of this experiment. So we're going to calculate this. We're going to also calculate the yield in the next page. So let's move on. So let's start. We start with Fe3O4. So it's going to be 48.4 grams of Fe3O4. We want to convert this to mole. So it's going to be 1 mole of Fe3O4 will give me 240.55 grams of Fe3O4. We go to the next page. What's the mole ratio? between iron and carbon dioxide. There is 4 moles of carbon dioxide for every what? 1 mole of Fe3O4. And then, of course, if I cancel so far, you see grams of this cancel grams of this. Mole of this cancel moles of this. To finish it up, we want to convert moles of carbon dioxide to the mass. So what it means is that every mole of CO2 contains the molar mass, grams of CO2. And again, if we finish our cancellation and do the arithmetic in our calculator, it's going to give me 35.4 grams of CO2. That is exactly what I'm going to be getting here. We've not, so now it's now left for us to do the next one. For the next one, okay, since I made this thing for 2 pages because I know this problem was going to be a long one, I'm going to do it on the next page. If I go to the next page, continuing the same problem, it didn't change, to finish up the last 2 parts. So I'm going to solve for, I've solved for Fe3O4. I'm going to solve for carbon monoxide. So it's going to be, for, again, I have to go back to my usual color. 14.6 grams of CO. Of course, if 1 mole of CO will give me, earlier I told you it's going to be 28.01 grams of CO. And then 4 moles, what's the mole ratio? 4 moles of carbon dioxide to 4 moles of this. So it's 4 moles of CO over 4 moles of CO2 to 4 moles of CO. And then again, the molar mass, 1 mole of CO2 will give you 44.01 grams of CO2. And then if we do our mathematics very well, if we cancel out this, we cancel this, this, we cancel this, and then this is going to cancel this. And then if you do our math very well, it's going to give you 22.9 grams of CO2. Now, I go back. So I want the one that gives me the lowest to be my theoretical yield. This gave me, from carbon monoxide, I got 22.9 grams of CO2. And then from Fe3O4, I got 35.4 grams of CO2. What that simply means is that my theoretical yield is, this is my theoretical yield. So the theoretical yield of this experiment is, this is the theoretical yield. And this is where I'm going to calculate my percentage yield from. Remember the formula I gave you. And of course, the limiting reactant is what? So you say CO is the limiting reactant. CO is the limiting reactant. And then from there, I'm not going to calculate my percentage yield. So what is the, remember the percentage yield formula I gave you earlier? The percentage yield formula simply says the actual yield, actual over theoretical times 100. That's what it tells us. So what that simply means is that my actual, said the second question says, what is the percentage yield if the actual yield was actually generated? So we're going to say 17.2 grams divided by theoretical yield we got is 22.9 grams. We're going to multiply that by 100. And when you do arithmetic well, it's going to give you 75.1% carbon monoxide. And this becomes our percentage yield. This becomes the percentage yield. So I can write this full, the percentage yield of this experiment. So you can always pause this video and try out the next problem. The next problem also addresses both the percentage yield of limiting reactant. So this will definitely be the last problem we're going to be doing today. So let's take it off. It says, how many grams of water are made if 31 grams of ammonia react with 35.3 grams of oxygen according to the equation below, which is the limiting reactant? And it also says on the second part, what is the limit, what is the percentage yield if 20.9 grams of carbon monoxide we had isolated. This is so this is, remember, this is our actual yield. So we're going to start immediately. The molar masses of everything I need. So the molar mass of this guy, of ammonia, is 14. Oh, now I'm not going to calculate it. I'm just going to give you what it is. It is 17.04 grams per mole. Remember, I calculate my molar masses with 2 decimals. 2 decimal places for the relative atomic weight of element in the periodic table. Then my oxygen, of course, I did oxygen so many times here. Oxygen is 32.00 grams per mole. And then finally, what else do I need? I need water there. My water is 18.02 grams per mole. Having done those, we now start. First of all, we start with ammonia. If I start with that 1.0 grams of ammonia, I want to convert from grams of ammonia to grams of water. That's what I want to do. So again, it's going to be 1 mole of ammonia. Of course, a mole of ammonia will contain 17.04 grams of ammonia. And then again, what's the mole ratio between ammonia and water? It is 6 moles of H2O. 6 moles of water is equivalent to 4 moles of ammonia. And then lastly, I want to convert to mass of water. To take away this mole, 1 mole of H2O will give me 18.02 grams of H2O. And what that simply means is that if I cancel this goes with this, this goes with this, this goes with this. And if you do my calculation right, if you do yours right, you're going to get 49.2 grams of water. That is only from ammonia. Now, we're going to go for it from oxygen and see what we're going to get. If I go for it from oxygen, I want to move this thing a little bit up, just not to cover the problem. So if I go from there for oxygen, I can do it in the next page as well. Okay, it doesn't matter. Let me do it here since I already wanted to create this space. All right. Oh, I go to the next page. I can just do it in the next page. Yeah, I can just do this in the next page. Okay. Yeah, I think this space might be reasonably okay for me to feed this in. It's just that I don't want it to cut. Okay, let's see what happens. I can feed it in here. So again, I start 35.3 grams of oxygen. So it's going to be 35. I'm going to change the color. 35.3 grams of oxygen. So I'm going to have 1 mole of O2 contains the molar mass, that's 2.00 grams of O2. And then from there, what's the mole ratio between oxygen and water? There is 6 moles of H2O to 5 moles. This is 5 moles of O2. And then from there, I have to convert it to mass of water. The mass of water is going to be, of course, let me cancel first. Always good to cancel as you go along the line. That keeps you on track. So if I go back to my color, a mole of H2O, of course, will give 18.02 grams of H2O. And then if you move from there, if you do your calculation right, you're going to be getting, of course, let's try to cancel the last one. This, we cancel this. You're going to be getting 23.9 grams of H2O. Now, I think we're coming to the decision time. Between these two numbers, this is the less number. Of course, the lower number will give us the theoretical yield. So let's go to let me now go to the next page. So now, what it means is that the theoretical yield I got there is, my theoretical yield is 23.9 grams of H2O. And why did I get that? Because oxygen is the limit. Look at this. Here, oxygen yields that. Oxygen yielded that. Therefore, oxygen is the limiting reactant. So the limiting reactant, I can write it full. Is oxygen. So now, what is our percentage yield? Our percentage yield, of course, I wrote the formula before. I'm not going to write it now. Percentage yield of this experiment will be, now we were given the actual yield to be 20. So it's going to be 20.9 grams of CO2 divided by, of course, what is our theoretical yield? The theoretical yield is 23. Like I always told you, the theoretical yield will always be greater than the actual yield. It is just always certain for that to happen. If that doesn't happen, there's a serious error somewhere. Because we're not living in a perfect world. No, this is water. Why am I even writing? Okay, I think I'm going to take this off with eraser better than to. I don't know why I'm writing this. So this is of water. We're talking about water molecule here. Where did that come from? 20.9 grams of H2O divided by 23.9 grams of H2O times 100/1. Of course, everything we cancel. If you look at this we cancel this, and the answer will give you 87.4 grams. No, not grams. Percent of water was generated in this experiment. And what that simply means is that some things we are lost. So this becomes the percentage yield. So you can always go back and watch this video and watch it again to get yourself very much acquainted. It's a video that you stay with and watch it anytime, and take your time, and as you watch it, I advise you to always take that note. So this is the end of today's lecture. Thank you once again for listening, and do have a blessed time ahead. Bye.